Okay, everyone, we'll make a start. There are still a few people arriving as I speak, but they'll hopefully not miss the main talk tonight. Thank you very much for joining us. I'd like to begin just by saying thank you very much to the University of Leeds for hosting this first hybrid event in the north of England. We've been, as you know, hosting lectures online over the duration of the COVID pandemic, and that's become very much a way of life, and that's a good thing because we've had lots of people join who otherwise might not. But the aim here is to try and kickstart hybrid events where we present online and in person. We have a small but select audience here in Leeds tonight. Thanks very much for joining us. On the admin side, I'm sure you probably have gathered that the fire escapes are to my left and right at front, and the main exit at the back. The bathroom, should you require it, is up to the left. And then on your right, but I'm required to say that by Claire, who's been very, very helpful, Claire Atkinson, in organising tonight's event. And thanks also to Harding, who's been extremely helpful with the IT side. Tonight's talk is presented by the Audio Engineering Society, as you know, and also joined by the Institute of Acoustics. Before we introduce tonight's speaker, I just wanted to say a couple of quick words about those two organisations. I'm presently the chair of the AES UK section committee. The AES was founded in the USA about 1948, so that makes it 75 years or more ago, and merged in the UK with the British Sound Recording Association. It's now a fully international organisation with 12,000 plus members. And 120 plus AES student sections around the world. So it's very much a global thing. We have international conventions in the spring in Europe. The next one will be in Finland next month. And in the fall, or as in the autumn, as we would say, in the USA. Conferences and regional events are held throughout the world and throughout the year on various different keynote subjects. So a lot going on in the way of conferences and publications, the flagship AES journal as well, of course. On a personal note, I joined the AES very shortly before embarking on a PhD in active loudspeaker control. And I have to say that without the AES, it would not have been possible to complete my PhD as I did it. Very, very valuable organisation. So please do consider joining us if you're not already a member. And on a local level, the UK committee is always keen to have extra people on board to help to organise events like this one, to spread the word about audio in the UK. We have lots of events coming up, as you've probably seen on the video in the background. The Institute of Acoustics, just to mention our partner organisation tonight, is a sister organisation for those working, unsurprisingly, in acoustics, vibration, noise. It's got about 3,000 members in the UK from a very diverse range of backgrounds, not only engineers and scientists, but people like lawyers, occupational architects, environmental health, that kind of angle on noise. And that gives rise to a very multidisciplinary organisation, very, very fertile ground for cross communication between different disciplines. And like the AES, that lively nature is reflected not only in its programme of events, but also in the specialist working groups and the standards and legislation development that the IOA gets involved in. It offers a route to chartered engineer status, if that's important to you, supported by CPD. So people can keep up to date with what's going on in both a rapidly changing professional and regulatory framework. And it also offers a number of courses, both remotely and at centres throughout the UK. So that's the plug. If you're interested in audio acoustics, and if you joined us this evening, which suggests you certainly are, then I would recommend both organisations to you, and you will be, I'm assured, I can assure you personally as well, very warmly welcomed indeed. Another admin point, we are looking very much forward to your questions tonight at the end of the talk. If you want to post them, please do in Zoom on the Q&A portion. There's a dedicated window for Q&A. Please use that, not the chat. And soon we'll be opening up the microphones in any case if you want to ask your question in person. With that, I'd like to introduce tonight's speaker to you. Jamie Angus-Whiteoak, Professor Jamie Angus-Whiteoak, Professor of Audio Technology at Salford University. She's been in industry and academia for very many years, started off in research at the Beats Marketing Research Laboratories.
Standard
Telecoms Research Laboratories, as was, forgive me. But in that, and I've known Jamie for probably about 15, 20 years now, her experience spans a bewildering range of technologies in audio, from everything from vacuum tubes, pulse code modulation, signal processing, diffusers, super audio CD, of which she was one of the creators or the inventors, 4-channel digital tape recorders. She's worked in signal processing, analog circuit design, and numerous other technology topics throughout the years. She's been active with the AES for 3 decades and has been awarded the Fellowship of the AES, the IOA Peter Barnett Memorial Award, and the AES Silver Medal for contributions to audio and acoustics. So we have a very special speaker with us tonight. It's a delight to introduce her to you. She's also an honorary fellow of the ISCBE, the Institute of Sound Communications and Visual Engineers. And to top it all, as if that wasn't enough, she's also the VP of the AES for Europe at the moment, and will be speaking as the Heiser Memorial Lecturer in Finland in about a month's time. So, Jamie, I've talked to you. Welcome.
Right. Hello, welcome.
Trooping
well, my slides will appear.
I will.
What is the peak of this signal? So, are we all agreed that we would probably, looking at this digital signal, say sample number 3 is the peak of the signal? There we are. It's actually neither, it's not number 3, it's somewhere in between sample 2 and 3. And as you can see, it is considerably larger than the sample value. And this is typical of what happens with digital signals. Peak's actually 0.7, and it occurs between the 2 samples at position 2.6. And this is not a fake signal. This is something that you could get out of a system. So what the peak value of the error is it's basically reading -3 dBs low. And because of that, if we were using that to control some form of gain circuitry, that would be a very serious error. It would either allow overmodulation of a radio transmitter and give you a very painful visit from the regulatory authorities, or you'd end up with clipping and other such like. And yes, I know it's used as a creative vehicle, but it probably wasn't what you wanted. So the underreading will matter. So the sample doesn't actually give you the true level of the signal. The other thing that might matter is the fact that that peak of that signal occurred between 2 samples, and that may also matter in some processing applications. So what we're going to do in this talk is unpack that. The sample values are not the whole story. When the audio sample waveform is sampled, the actual sample value may not be the actual level of the signal. Now, the thing about this is that we are so used to the Shannon-Nyquist theorem that we forget that there are terms and conditions applied. And the terms and conditions are that the system is linear and time invariant, i.e. there's no time varying operations. If we keep to those things, which counts for filtering and Fourier transforms, everything's hunky-dory. And the textbooks teach you all that. Unfortunately, for a lot of the processing we want to do these days, noise reduction, compression, all the fancy plugins you get these days to tart up your recordings, these conditions no longer apply. And one example of where this can break down is the simple aspect of working out the actual signals level. And we're going to use that as a model to unpack this. So what we're going to do is discuss the issues involved in this deriving the true audio signal value from the sampled audio and the pros and cons of various methods. And all being well, we'll then discuss how the knowledge of the intermediate sample values are required for other nonlinear linear operations. And hopefully by the end of the talk, you will understand what I mean when I say the samples truly are not what they seem. So we'll discuss the issues first in deriving the true value. We're going to unpack sampling a bit with that and discuss the difference between sampling and what I call reconstruction. We'll look at the various pros and cons of measuring the peak value, and we'll actually come out with a simple technique that provides accuracy with a fairly low computation delay. So we all know this, or a lot of us have seen this, but I'm going to start basic just in case you haven't. You know, the whole idea of sampling is we take some sort of wiggly analog signal and we only look at it at certain instantaneous points in time. For audio purposes, we tend to use a regular sampling grid, so we look at it at equal spaces of time, but there's no particular restriction on doing that, although it makes some things a bit harder later on. So assuming we're looking at things at a regular period of time, then we'll get on the left there's a square wave that's been low pass filtered edge, and we're going to sample it at regular intervals, and on the right we get a sampled version of that square wave. And you can see it preserves the basic shape of things, but it doesn't obviously preserve the bits in between. And of course, the Shannon-Nyquist theorem says that provided we sample that waveform fast enough, and we can consider it a bit like modulation, fast enough so that the highest frequencies and the copies of those higher frequencies that result due to a sampling process don't overlap, then we can separate, if you like, the baseband from the alias versions of that signal. And provided we can do that, we can say, yes, we can sample this signal without loss. Of course, in some cases, when we do that, those conditions aren't satisfied, and the frequencies that are copied up at higher frequencies effectively overlap each other at the top end of the band. And because of that, we get something called aliasing. And I've got a couple of demonstrations here, so if you'll bear with me, all being well, this will work. So here's a swept sine wave. Okay, and this is one where we've allowed aliasing to occur. Now you will notice that that was sampling the swept sine wave should have still kept going up in frequency, but you'll notice actually it didn't. It started coming back down again, and that was because it was aliased. And instead of hearing the higher frequencies, we started hearing the alias version coming back down, and that's an example of aliasing. One way of looking at it is that under those conditions, you've got more than one possible sample sine wave that fits that set of samples, fits the samples. So in fact, you can't reconstruct the original waveform. In practice, I mean, in theory and in practice, there's actually an infinite number that do, but we couldn't hear most of them. We could only hear the smallest one. And we can think of it a bit like Alice in Wonderland. It's like having a through the looking glass mirror at half the sampling frequency and another mirror at the frequency equals 0, and you have this sine wave. It's sort of like the start of a joke. A sine wave walks into a mirror, and a copy of one and walks back out. And in fact, if you were standing in one of these rooms with mirrors front and back, you'd see an infinite set of copies of yourself, alias copies of you, which suits some narcissistic personalities, but I find quite disturbing when I see it. So the result of sampling is we've taken the infinite frequencies of the real world and we've compressed it into a very narrow range from naught to the sampling frequency. And in fact, half of that is the conjugate copy of the other. So frequency goes from minus infinity to plus infinity, so actually collapsed onto a frequency of minus fs over 2 to plus fs over 2, or more conventionally, if you look in the signal processing books, 0 hertz to fs hertz. And in honor of COVID, I've got a little picture of this. 0% is all you have, and effectively, like a toilet roll, all the frequencies are wrapped around. And if you think of each page as being 0 to fs, you have alias copies. And this is true for any frequencies that are present in the signal you're sampling. So you really do need to constrain your input signal to have frequencies less than fs over 2. More subtly and less obviously, it also applies to any frequencies that you generate via distortion methods. So if you have a nonlinearity that generates frequencies higher than fs over 2, that too will create alias components that wrap round. So all in all, not a good thing to do. So we can also think about, so far I've sort of done it in a frequency domain approach, but we can also think of it in terms of the time domain. And if we're taking a square wave filter and putting it into a perfect brick wall low pass filter, which has a sine x over x response. And as you can see there, if you look at the picture on the right-hand side of that brick wall low pass filter, around each sample point, you've effectively got the impulse response of that brick wall filter. So the value of the signal at that point represents an average, weighted average, according to sine x over x, of all the points described by that sine x over x impulse response. They've all been averaged together to form the value of that one point, the output of the filter. And because of that, we actually look at the sine x over x signal. It actually, unfortunately, goes from minus infinity to plus infinity, which gives us some other problems that I'm not going to discuss today. But the important thing about it is it crosses zero at all sample times other than the central sample point, the central main lobe. You'll notice that that signal actually does, it's probably easier to see there. You'll see it's zero there, and for all subsequent time shifts, it's zero. And when you cross multiply it and look at the cross correlation, you'll find that the signal is actually averages to zero for all possible time shifts other than zero time phase shift. So time shifted versions of this sine x over x impulse response are orthogonal to each other. In other words, we can look at them. Orthogonal is a fancy way of saying they're like 90-degree coordinates. We can say, look at the sample values as coordinates, and here's an example for 3 samples because I can draw that. Because they're orthogonal, each sample or set of samples specifies a unique point. It was a whole message and endpoints. It would specify a unique point in multi-dimensional space, and that point contains all the information we need to know about the signal. And in principle, it's reconstructable. For filtered noise, where the samples are independent, we can actually say that the information content, the rate of innovation is actually fs, or 2 times the bandwidth. So long as we sample at 2 times the bandwidth or greater, we're going to preserve that information. Right, so that's sampling. So sampling effectively with a band limited signal lets us specify a coordinate in space that uniquely specifies our input signal. That's half the problem. What we then need to do is to get our signal back, after doing this process, is to reconstruct it. And that reconstruction, again, we can look at in both frequency domain and time domain viewpoints. So typically we talk about it, sometimes it's referred to as an anti-alias filter, which it isn't really, it's a reconstruction filter. And I think that's quite important to get a hold of. Anti-alias filters happen at the input to restrict the frequency range of the signal. What a reconstruction filter does is actually, if you like, fills in the dots between the samples that you put into it. So if we do it in terms of the frequency domain, the usual way of thinking about it is we're removing the copies, the high frequency copies of the signal, which effectively specify our little spikes that are coming out of the system, and use that filter to smooth between the two, between the samples. And so long as there's a gap between those higher frequency copies and the original baseband filter, it's fairly straightforward to filter them out. And ideally, perfect low pass reconstruction filter. And we can get something that leaves us with the original baseband of the signal. Right. Again, we can look at this in the time domain as well. And this is quite helpful to look at it in the time domain. And what we're doing there is we have our sampled signal on the left there, which is just a series of spikes. We put it into a perfect low pass filter, which has this sine x over x impulse response. And essentially what we're doing is we're replacing, for each sample on the input signal, we're replacing it with a sine x over x copy. So we get sine x over x plus shifted version of the sine x over x, and so on and so forth. And again, the original sample replaces replace the impulse response to the original input signal. Because they cross over at 0 at every other sample point except the central point, again, those results are orthogonal to each other, and it's fairly easy to show that by linearly combining them, you will get a smooth version, the original signal back. There, again, as I said, there are some issues associated with the infinite nature of this impulse response, and papers by Unser et al. Discuss ways of getting around it. Another way of looking at it, just to make quite clear point about replacing each point, we're sort of think about it as an impulse response, overlapping diagonals there, triangles add together. We're effectively replacing each sample with some form of impulse response, ideally a low pass filter, perfect low pass filter, and we'll get some sort of reconstruction of the signal. And there's an example of lots of overlapping sine x over x's, and you can see there that they peak up at each sample point, but in between sample points, you'll notice that they all are 0 at adjacent sample points. So this is what allows us to add things up and reconstruct the signal. And again, effectively, we can think of it as a coordinate system, and where it's like reconstructing the original signal on the basis of that single point specifies the sine x over x sizes of the individual coordinates, so that when we add them together, we get our original signal back. Okay, and that's just a pretty picture of a reconstructed square edge, just to show you that it happens. Okay, so let's get back to level detection. And level detection, peak detection, is something that happens a lot of the time in lots of different circuits. It's used for all sorts of things. I've got on the left-hand side, a analog sort of level detector. The idea being when DT goes higher than the charge on the capacitor of the envelope, that MOS transistor will switch on, and the net result will be the capacitor charges up until they're equal, which point the transistor will switch off. And you'll get a waveform shown in the diagram on the left B, where you follow the waveform till it gets to the peak and then hold there, and the I discharge will discharge a little bit till it comes to the next peak, and so on and so forth. And if we look at the bottom right-hand corner of that slide, there's an example piece of software code that we might use for trying to detect the peak based on sample values alone. But the software doesn't get it right because all the software can see is the sample value. So the big difference between the software and the analog version is the analog version sees the whole waveform, whereas the software can only base it on the sample values. And as we saw earlier, that can be wrong by quite a big margin. For my earlier example, it was about 3 dBs, but it actually can be worse than that. So here's an example. This is a band-limited impulse. So this is what would come out if you threw an impulse response into our perfect low-pass filter. We'd get something that looked a little bit like that. So this is the torch track signal. This is the worst case, but a band-limited impulse. So if everything's in phase and the sample aligns with peak of the sine X response of our perfect low-pass filter, then actually there's no error at all. We capture the peak perfectly. So what's the problem, Jamie? Well, the problem is we can't guarantee that. We have no idea what the relative phase of the sampling instant to the input signal would be. So what happens if it's shifted by half the sample in terms of the relative phase? Well, actually what comes out of the system now is 2 equal valued samples on either side of the peak of the impulse response, and there will be an error. The sample value is not the peak value of the impulse. It's less than the peak value of the impulse. And in fact, it's actually 0.64 instead of 1. That's a minus 4 near enough dBs of error. So it significantly underestimates the actual size of the peak. Why does this matter? Well, let me give you an example which has actually caught out quite a few engineers designing high quality digital to analog converters. What happens if you put a square wave into one of these systems and you've got your expensive D2A converter and you want the best signal to noise ratio? So of course you set plus max and minus max of the D2A converter output to plus and minus the maximum capable output voltage of your analog circuitry. You check it on the digital bit, it works fine. You get the maximum output, the minimum, maximum negative output, everything looks fine. You then put it into a low pass reconstruction filter, and what you get is the blue waveform coming out of there with an overshoot. And of course, because you're already using the maximum supply voltages, that waveform runs into the end stops and you get clipping. And there have been products that have gone out as far as market where people have said, oh, that doesn't sound good. And when they've investigated it, what they found is exactly that's happened. Because the output of the D2A converter has been set so high for, not unreasonable reasons, they forgot about the overshoot that happens when you put it through a realistic low-pass filter. And you either have to back off the level that comes out of your D2A converter to allow the peaks, and this is still something that's being discussed. For example, PA systems, how much margin do you allow in peak power output from the PA systems above and beyond the maximum output of your D2A converters so that you're not clipping your PA system? And the answer is probably you need about 1.5 dBs or so of extra margin, which when you're talking about kilowatt systems is not trivial amounts of power to actually get around that. So that's why the value between the samples matters, because it's the value between the sample that's causing the clipping, not your actual samples themselves. So what do we do about it? If we're trying to detect peak levels, what can we do about it? Well, one obvious way of doing it is to increase the sample rate artificially, keeping the signal content the same frequency range, but actually having more samples per interval. So here's a very simple thing. It's called a polyphase interpolator. The idea is you have n filters. They're actually slightly different phase-shifted versions of the same filter impulse response. You feed the same input sample to all n filters, and then you successively, switch between the different outputs. So for each input sample, you produce n output samples, which progressively fill in the gaps in between the adjacent samples to give you n times the interpolated output. It's actually computationally not too bad. Something you can implement these days fairly readily in software, and it works quite well. Here's an example of it working just with a factor of 2. So you start with your original sample rate. This is going to be raising it by a factor of 2, so n equals 2 in this case. Stage 1 is to add some 0 samples in between it. Nominally, that's theoretically what you're doing. And then you filter that resulting signal to fill in the gaps, and that gives you an interpolated version of the input. An example that uses this 4 times is actually often sufficient to do a reasonably good job of capturing the peaks in a signal. An ITU 77-4, which is the loudness meter, used in quite a few applications on the web and things to do loudness normalization, actually has a specification for 4 times over sampler, which has 4 times upsampling. It actually introduces, though, there are some costs to it. One, it introduces about 6 samples of delay to the whole system, which, if you're just doing straight through, which the application is useful for driving a peak level metering system, isn't a problem. But it is a problem if you may want to use that output fed back to control something. And although the computation isn't large, it's not trivial either. So it actually involves 48 multiply adds to actually do it. And that's 48 multiply adds per input sample. So there is a computational cost, and there is a computational, well, actually not even if you had infinite computational speed, there is a delay because you've got to delay enough of the signals to do the filtering, to do the interpolation. So it's not cost-free. And in some applications, and here's one, classic, you want to emulate some of the vintage equipment. Well, vintage limiters and compressors, quite a lot of them use a technique known as feedback limiting or feedback compression, where they took the outputs of the gain control device and they looked at this level. When it was above a certain threshold, so they would detect the level, check against the threshold. If it was above that threshold, they would then reduce the gain. Very simple to implement in terms of analog circuitry. You could actually do it with almost with one valve, but on the order of that sort of complication, one light dependent resistor, one valve, and some form of rectification device. Fairly simple to implement, fairly classic sound, but involves feeding back the output and the level of that output into your gain control device. Now, if you've got a delay of 6 or more samples on your level sensing device, that is not going to work so well because you're having a significant delay into a feedback loop. So it's unlikely to work quite how you expected, and certainly not like the piece of equipment you're trying to emulate. So in these circumstances, you actually want to get the level faster. And then we have some interesting problems because we want to work out the true level of the signal with less samples. And we've already seen the samples are not what we need. We need a reconstructed signal between the samples. So one way of doing it is to do something called parabolic interpolation. That takes 3 samples. The overall delay of the system will be on the order of 1 sample. And the idea is you use those 3 sample points to construct a parabola through it. And you use it to calculate the position of the peak and the height of the peak. And it's fairly straightforward. You can sit down with the maths. It involves solving some set of simultaneous equations, but actually once you work through it all, it comes out with two sort of equations that give you everything. So if we've got three values, call them alpha, beta, and gamma of the sample in the center and the sample before and the sample afterwards, you can fairly readily calculate the position of the peak as a algebraic equation, fairly straightforward one of those three values, and you can calculate the peak also as a fairly straightforward algebraic combination of those three values plus knowledge of the position. So you do have to do both calculations, but they're not onerous and they will give you quite a quick estimation of the peak amplitude of the signal. I do have to say though, that will not work all the way up to the highest frequency. It does underread a little bit of the higher frequencies, but it underreads less than just using the sample value. Once you go down about 2/3 of the highest frequency, it gets reasonably close to the right value. Right, so quadratic interpolation is an alternative way of getting, if you like, the true peak of the signal rather than the underestimate you get from the sample values. That's applying it in the time domain to a time domain signal. Some of you may want to look at peaks in the frequency domain, where you do the Fourier transform, you look at the magnitude. Seems to be quite a popular thing in artificial intelligence and machine learning these days, is to find things like pitch peaks and things, stuff like that. You can do the same thing to do frequency peaks. I remember doing this in the 1980s for a pitch detector. I actually used parabolic interpolation to work out the pitches of various things, speech signals, and you can use it in the frequency domain. And there's some nice little things here for you use it for frequency domain peaks. If you use Gaussian window and you can actually do a little bit of a trick with the Gaussian window is infinitely long, so you need to chop it off. But you can actually do the trick Hamming used with his window to add a little DC step of 9% and get cancellation of the two nearest bins, which is kind of useful for separating pitch bits. But the really important bit about it is that the log magnitude of that peak, because it's a Gaussian window, when you analyze it through, which is Julius Smith of CCRMA did, you can show that it's actually parabolic in shape. So a parabolic interpolation of that peak is actually a really accurate match to what's actually happening. You do need to add zeros into the original signal before you do the Fourier transform, so you do interpolate up a little bit, but 2 times is usually sufficient. And the net result is you get actually quite a good estimate of the position, which is often what you want, as well as the value of the peak. So that's another application of quadratic interpolation. Finally, we didn't talk about it much, but nonlinear operations, and this is a real humdinger. Nonlinear operations really should be applied to the reconstructed waveform. And here's an example of the original signal I asked you, what's the peak of? And I've just squared it. Now, this is something you might do, for example, trying to find the root mean square of this signal. First thing you do, square. So this is a signal squared. I want you to notice something quite interesting. One is that if we look at it, the peaks of the signal they're sampled sort of approximately near the peaks of the signal, but it's not sampling at all at the valleys of the signal. So what would come out of this is something that looked pretty much like a slightly bent line, but definitely not having the wiggles that are in the original signal. So you would get a result that really doesn't match what's there in terms of the mean square value of the signal. In other words, you get an error. I don't know which direction it would be, but parts of the waveform are missed. I think it would have probably overestimate the RMS, looking at it, I'm just eyeballing that, but I couldn't guarantee that. And parts of the waveform are missed between the samples. Now, the only way to solve that would be to interpolate up by a factor of 2 or 4 so that you actually did catch those samples. And what that means is, again, even for something like an RMS detector, the likelihood is that certainly the high frequency portion of the frequency range your device is supposed to be working with, unless you have done interpolation, you are not going to get the right result by just looking at the samples. You need to reconstruct the original, if you like, the original waveform. So, to conclude, the ability to measure and control an audio waveform level is actually quite an important part of a lot of the stuff we do. You know, if we're doing noise limiting, or if we're doing noise reduction, where we're trying to check levels within bands. But because the audio waveform is sampled, the actual level is not necessarily the sample values. In fact, it's more likely not to be the sample values. But what you want is an intermediate value between samples. Nonlinear operations won't work as expected. Actually, dynamic variations in levels are also affected because you're pulling down things at the sample times when the actual peak of the waveform is different away from the sample times and maybe higher. So again, when you look at the output waveform, it may not be what you would quite expect. So it wouldn't match what you would have got if you'd operated on the continuous waveform. Various methods can be used to ameliorate the upsampling is one popular method. Quadratic interpolation is another. And as I said beforehand, the samples are not always what you see. Thank you. And I'm open for questions. Right, so this is always a perennial question. Usually, how do you get the back the information between the samples? Is it all those sin x over x's? Right, Eric. Yes, it's the sin x over x's. So, because we use, and again, when you look at, if you look at Nyquist and Shannon's original paper, they say, provided we have a sin x over x low pass filter response, then because it only peaks at that center sample, and if I move it one sample over, then, you know, if I try and correlate this one, which is shifted by one sample compared with this one, those two are orthogonal to each other. In other words, I can vary the amplitude of this one. It won't affect the amplitude of this one, and vice versa. What that means is that when we add them back together again to reconstruct the signal, then that fills in the gaps for us perfectly and accurately. So it actually is very much so that the sin x over x behavior of the perfect low pass filter is one of the reasons, if you like, why this whole thing works. And that's one of the terms and conditions. Now, one of the interesting things that's come up, you know, since the 80s is various people have said, okay, that is a way of doing it, but one of the problems with sin x over x is that it essentially stretches from minus infinity to plus infinity. You know, the universe hasn't been switched on that long. So we have a real problem in terms of making it suitably accurate. And there are alternative approaches using splines and other techniques. There's actually an open access paper in the AES journal published 4 years ago, 5 years ago. It's got my name on it, but you can download it even if you're not an AES member, which is an introduction to modern sampling theory that unpacks some of this. But yes, you can get the intermediate values. So it's not a case of the timing is not affected. You can recover the original timing. In fact, if we go back to the slides, let's see if I can just rattle back to the slides. One of the slides I showed, let me just show you the big square wave there. There's that one. Well, if I get rid of the little pop-up thing. Right, there we are. If you look at this, this is an example of a sampled square wave, the edge of, and you'll notice that the zero crossing is in between sample values. And I mean, that red line is what you can reconstruct from those sample values. You'll notice it passes through zero in between sample values, i.e. its timing has been preserved at the, if you like, micro timing sense. So the fact that you've sampled it every 22 odd microseconds doesn't matter. It actually still captures the timing, because the miracle, if you like, happens because of the orthogonality between shifted versions of the sine x over x. Hopefully that answers your question. If it doesn't, drop another comment back in the right. So using different filter types. Yeah. So I'd recommend you look to the tutorials. A modern sampling, a tutorial is what it's called. There is a technique where you combine, if you like, a filter at the input of the process and a filter at the end of the process. Right? Turns out sine x over x is the only filter that you can apply singly, either at the input and the output. So that's kind of a pain. But you can use two different filters combined together, where the combination of the two filters, they've got a bi-orthogonal relationship. So when you combine the two together, they form an orthogonal filter set. And it's, as I said, it uses splines. So actually gives you quite a nice reconstruction technique that doesn't have overshoots. It's very popular with the radiographers and X-ray people because it doesn't have overshoots or undershoots, which tends not to happen in video. So there's a bit of a problem. So it's like, right, so 96 hertz, going up higher in frequency. We've got to remember that the reason we chose 44.1 and 48 kilohertz was because that's what we could do with videotape recorders back in 1980. Speaking to someone who actually invented a 4-channel digital tape recorder in that sort of time frame in the late 80s, we were pushing the technology. You know, video recorder storing digital stuff was basically about the limit of what you could do with the technology. And because of that, we could fit so many samples per TV line, and that pretty much gave us 48 kilohertz or 44.1. To be honest, I don't think anyone really said that's the best we could do. It's what we could do, not necessarily what we want to do. And whether you need to go to 96 kilohertz, once we started with 44 or 48, it sort of became automatically, because it's easier to double it than to go fractionally. I know Bob Stewart of Meridian has done presentations where he suggested actually a rate of something like 60 or so kilohertz would give you that little bit more space to filter things out. So 96 kilohertz sampling rate does make it easier to pick up peaks. Still not quite enough to do it just via oversampling, but it would certainly, if you're using quadratic interpolation method, be, you know, the signals that don't go above 20 kilohertz, that would be fine. So a bit more data, but these days data is fairly cheap. So yes, it solves a few problems. I mean, it gives you a bit more space to put filters in the gaps in between. It makes reconstruction a little bit easier. Of course, it does use double the data rate. Perceptually, to me, it sounds more open, but that's very much a subjective judgment on my basis. Oh, that's a good. Right, let's see. Okay, JD Wong. Different true peak meters and limiters can give different readings. How do you evaluate how good a true peak meter really is? Personally, I think the only real way of doing it would be to properly reconstruct the waveform from the samples, which means doing some form of ideal reconstruction, and then, you know, working out what the peak level from that would be, and then looking at your peak level meter and say, you know, do a straight XY comparison, say how close does it match it. I know when they did the 1770 standard, Gilbert Soulouze did spend quite a bit of time matching subjective responses to the loudness responses, but that wasn't the peak meter, that was the actual loudness portion of the system. Hopefully that's answered your question. Is that all the questions? Any more questions, people? We still have time for some questions, I think.
Where did the audio come from at the beginning and the end?
Sorry?
Where did the audio beginning and the end of the presentation come from? Not familiar with it.
The audio at the beginning of the talk. Okay, so I have to say, the title of this talk actually came, the final exercise I used to give my students was to look at the standard and design a loudness meter to work at 44.1 kilohertz. The standard's written at 48 kilohertz. So it's actually a bit of a challenge to work out which things you have to scale to account for the different sample rate and other things like the oversampling filter you don't. One of my students handed in this report, which I can't remember the exact title, but it said True Peaks. And then it said, there's something are not always what they seem. And I basically slightly modified it. It's from the Lynch series, Twin Peaks. And what you heard at the beginning and the end was the theme song from Twin Peaks. And there are owls in Twin Peaks. I didn't put up pictures of owls, but you know, various theories about what the owls were abound, but they were not what they seem.
Okay, the music is by Julie Cruz, I think.
Sorry?
The music is by Julie Cruz.
I thought
if you wish to look it up as a piece of music, it's Julie, Julee, Julie Cruz.
Oh, okay.
I have it on a CD somewhere, at 44.1 kilohertz somewhere.
Yes.
Which leads to the next question.
Eric, I thought 44.1 was chosen as being twice the frequency of human hearing range, the minimum needed by Nyquist. Well, that was factored into it. I mean, actually, to be honest, the first ever sampling rate that was chosen was 38 kilohertz, because that's what we used to use for the FM subcarrier for FM stereo, which gave you was also effectively a sample-based type system, certainly in the decoders. Yes, that was one of the factors, but really the reason it was 44.1 was because you can get 6 samples on a TV line at 44.1 or 44.056 if you're American, fitting on a TV line. And unfortunately, you can't have half samples, a bit like being half pregnant. It doesn't work. So obviously, if the numbers had come out significantly lower than our highest hearing frequency, people would have done that, would have chosen a lower frequency. So yes, if you like, it's set a lower bound, and 44.1 kilohertz really was fingernail, the minimum frequency you get away with. But what was driving was the video recording technology of the day. I mean, the original Decca tape recorders were based on quadruplex machines, working on fairly wide tape. I can't remember whether they had more lines or it would before the blanking period, but essentially they let you have a slightly higher sample rate. So they used 48 kilohertz because that gave them a bit more space. But 44.1, was pretty much predicated on machines like the Sony F1 and other machines using standard video cassette technology of the time, helical wrap, and they pretty much couldn't go any faster. You couldn't run it, say, 7/6 higher because the machine wouldn't take that. 44.1 was something that fit both the human hearing system and the videotape machine. Okay, Dave Jones has asked, I understand analog models are used in VST effects using an analog model-based gain control. Can this offer any improved peak level accuracy without delay? I don't quite see how. You're going to have to get some sort of estimate of the reconstructed waveform. The hint here is in the word analog. If it says it's analog, then the implication is that they are somehow generating a facsimile of the reconstructed signal to control and to use the control. I know some people are actually, if you like, instead of pulling sample values up and down or pulling up and down sine x over x type impulse responses and adding them together to get a more realistic result of their gain control. But to estimate the level, you're still going to have to estimate that reconstructed waveform. And to my mind, you either go for oversampling, and of course, nothing to stop you doing that, especially in an offline process. You could take your entire file, music file into VST or your digital audio workstation, upsample it to crazy times. It's a bigger file, temporary file, but now you've got a super upsampled version, and then run your effects stuff on that oversampled signal and do the necessary adjustments with quite a good estimate with low delay. I mean, a low delay in terms of the signal, but it's not low delay in terms of real-time stuff because you've had to store the whole file. And that would do quite a reasonable result. If you're doing live stuff, though, digital live stuff, as I used to say to my students, you can't have a delay and then la 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 coming out much later. It just doesn't work. I mean, for a start, she'll kill you because a monosyllabics is delayed, and it just doesn't really work. So you're going to have delay to get an accurate estimate of the reconstructed waveform. Whether you can hide that delay because you're doing it all offline in a mastering or processing process, which for something like VST is pretty much what you're doing, and that's fine. If you're doing something live, then that's a different ball game. So it's one of these horses for courses. For mixed down track, you can do it one way, but if you're doing it for live, you might have to do it a different way, and accept that it might not be as accurate for the real-time thing, but as long as it's good enough, that might work. What else? Not seeing any more questions. I guess. Oh yes, there is. There's still. That's Eric. All right. Thank you, Eric. Yes, they are. I mean, they are connected because we piggybacked on your video machines because they were the only things that could record bandwidths required in the 80s. I mean, I can actually remember going on my birthday as a treat. My boss let me go to a meeting in London on digital audio recording, and we had the Iron Decker, and they'd only really just started using the quadruplex machine and flying around and recording, classical orchestras using it. I think it only did 2 tracks at the time. They had a stereo digital tape recorder, and it was, too heavy to lift. But as they said, it could fall off a plane at New York and be ready to record the New York Philharmonic, the next day. But yes, those rates are intimately related. So,
Any other questions?
yes, any more questions from inside? Going once, going twice. I think we may have got through all the questions. Can I say to people who came here, thank you very much, and to all of you online, thank you also very much. It's been great presenting things to you over the years, and I've really thoroughly enjoyed it. Cheers.
Thank you, Jamie. And I think that concludes our AES IOA lecture for this evening. Just a reminder, for those of you who aren't attending the next AES event, which will be in Espoo in Finland next month, I think our next event is in June. And please check the AES website for dates of forthcoming events.
Yes, okay.
Thank
Finland.
And thank you all again to our audience here in Leeds who've made the journey, in some cases, a considerable distance, I note. Very nice to have you here. And it's a small group tonight, but nevertheless, let's hope this is the beginning of well-attended hybrid events in the future. Thanks all again, and a very good night to you. Thank you.
Yeah. Please feel free to come down and have a chat.